Alright, hello everybody. We've got a new circuit to analyze. The problem states that we want to find the voltage VA in the circuit below using the node voltage analysis method. So let's take a look at the circuit a little bit. We see that VA is the voltage drop across the 20 ohm resistor in the circuit. We see that we've got two other resistors in the circuit. On the left branch we've also got a 9 volt constant voltage source, and on the middle branch we've got this dependent voltage source with the voltage of VA over 2. So the actual goal of the problem is to solve for this voltage VA, and we're going to do it using node voltage analysis. So what's the first step? The first step, as in all node voltage analysis problems, is we want to label all the nodes of our circuit. And that's what I've done right here. Notice that there's only one non-ground node in our circuit, so I've labeled it V1. Let's call it node 1, and let's call the voltage at V1. So I label it V1. So what's the next step of the problem? Well, typically you would go ahead and do your Kirchhoff's current law equations at that node, but since we've got this dependent source, and since we're solving for VA itself, let's see if we can create an expression for VA. So step 2 is we're going to try to solve an expression for VA. So what I want to do now is I want to isolate the left branch of the circuit. I'm not going to change it. I'm not going to do anything. I'm going to isolate the left branch of the circuit just so we can focus in on it. Okay, so now here's what I've done. I've isolated the left branch of the circuit so we can focus in on it and see if we can find an expression for this voltage drop VA across this resistor. Alright, so let's take a look at this resistor in this circuit. So to the left of our resistor we have a voltage of 9 volts, and to the right of that resistor we have a voltage of V1. Let me convince you on that a little bit more. So to the left of our resistor, first on below we've got ground. Then going upwards we have a 9 volt voltage source. So above that 9 volt voltage source we know that we have a voltage of 9 volts. So that means to the left of our resistor we have a voltage of 9 volts. To the right of our resistor we know we have our node. So we know the node voltage there is V1. So that means we've got 9 volts to the left of our resistor, V1 at the right of our resistor, and we know that we've got a voltage drop from left to right of VA. This tells us that 9 volts minus VA is going to be equal to V1. And that's what I've written here. 9 volts minus VA is equal to V1. 9 volts, which is the voltage on the left of the resistor, minus VA, which is the voltage drop across the resistor, has to be equal to V1. And if we isolate that expression for VA, we see that VA is equal to 9 volts minus V1. Okay, this gets us closer to the solution of the problem because we know the problem is we're solving for VA. So if we can get an expression for V1 and plug into this expression, we've finished our problem. So let's try to do this. Let's solve for V1. And the way we're going to solve for V1 is by performing KCL at this node in the circuit, at the node 1 in the circuit. So I've gone ahead and drawn currents at that node in the circuit, V1. I've got current I1, I2, and I3 as all going out of the node. And we know that by Kirchhoff's current law, the sum of all outgoing currents at a node must be equal to 0. The sum of all outgoing currents at any node in the circuit must be equal to 0. So that means I1 plus I2 plus I3 in the circuit must be equal to 0. So now we need to find out what is I1, what is I2, and what is I3. So those are our next steps. Let's first solve an expression for I1. Now I'm going to do the same thing that I did last time by just isolating the left branch of the circuit just so we can focus in on it again. Now we're trying to find I1, this current through this 20 ohm resistor that's going from right to left. So the way we do it, I've got an expression. The current through a resistor going from right to left is equal to the voltage at the right of the resistor minus the voltage at the left of the resistor divided by the resistor. And I've written that right here. V right minus V left over R is equal to the current through the resistor going right to left. So in our particular circuit, we've got I1 is going to be equal to V1, which is the voltage at the right, minus 9 volts, which is the voltage at the left, divided by 20 ohm. And that's going to be our expression for I1. So now we're going to do the similar thing, and we're going to similar thing with the middle branch, and we're going to find the current I2 going through this 10 ohm resistor in the middle branch. So this is a current that's going from top to bottom. So the current through this resistor going from top to bottom is equal to the voltage at the top of the resistor minus the voltage at the bottom of the resistor divided by the resistance of the resistor. So in this circuit, we're going to have an expression of I2 is equal to V1, which is the voltage at the top of the 10 ohm resistor, minus VA over 2, which is the voltage at the bottom of the 10 ohm resistor, divided by 10 ohms. Now that's going to be our expression for I2. And we're going to do a similar thing for I3. We've got a current going through this 40 ohm resistor going from top to bottom. So we've got the voltage at the top of the resistor of V1, a voltage at the bottom of the resistor of 0 volts rather, because it's grounded. And I3 is going to be equal to V1 minus 0 divided by 40 ohms, which is V1 over 40 ohms. So now our KCL expression, which is I1 plus I2 plus I3 equals 0, gives us V1 minus 9 volts over 20 ohms plus V1 minus VA over 2 divided all by 10 ohms plus V1 over 40 ohms is equal to 0. So that's our KCL expression. So now step 4 is going to be to plug in our known expression for VA into this KCL equation. And that's what I've done right here. So now we have we got the equation all in terms of V1, and we're going to solve for V1. So multiplying each term in the expression by 40 gives us a level, all terms on level. That's multiplying by the least common denominator. And if we keep doing our math, we're going to find that V1 is going to be equal to 4 volts. V1 is equal to 4 volts. So that's perfect. We've solved for V1, but we remember we're trying to solve for VA in this problem. So that's when we're going to go back to our expression for VA. So step 5 is to plug in our answer for V1 into our expression for VA. And our expression for VA was 9 volts. VA is equal to 9 volts minus V1. So 9 volts minus 4 volts is going to be equal to 5 volts. So 9 volts minus V1, which is equal to 4 volts, is equal to 5 volts. And that's the answer of our problem. VA is equal to 5 volts. So VA, which is the voltage across this 20 ohm resistor, is equal to 5 volts. All right, so that's what we've just done. We labeled all the nodes in our circuit. Then we found an expression for VA. Then we performed KCL at all the nodes in the circuit. Then we plugged in our expression for VA into our KCL equation. Then we plugged in V1 back into our expression for VA. And that solves VA. VA is 5 volts. Thank you very much for watching. I'm hoping this was of great help.